So now that we have understood, or I've told you, the definitions of relative isotopic mass and percentage abundances, we could then see how that apply to the calculation of relative atomic mass. Before we start, I just want to give you this diagram as well, which this is prepared by IUPAC. They don't just give you really absurd naming rules. They also are responsible for summarizing all the different isotopes and all the different percentage abundances of each element. And they come out with a report like every 10 years to update on any new isotope that has been discovered. It's actually a pretty good read. But if anyone want to have, this is an interactive periodic table, you can go to this link and then you can read it. It's all color coded. It's very nice. I'm not being sarcastic, by the way. I actually am quite impressed. Anyway, let's go back to the definition of relative atomic mass. So we'll talk about the fact that it is the weighted average of the relative isotopic masses of an element on the relative scale, where carbon-12 is 12 units exactly. So we'll talk about these two concepts of relative isotopic masses and relative scale. Now let's go back to the idea of the weighted average. I'm going to use the chlorine example again. So let's say if I have 40 chlorine atoms, around 3/4 of them, or 30 atoms will be carbon 35, sorry, chlorine 35, and the other remaining 10 will be chlorine 37. So if I want to calculate the relative atomic mass, I basically want to take into account both the relative isotopic mass of each isotope as well as the percentage abundance of each isotope. So if I want to come up with one number to represent the mass of chlorine, you need to take both of these into account. And the relative atomic mass of chlorine, basically, in order to work this out, you need to calculate the weighted average or the mean. Does anyone know what the mean is? Did you learn this in year 10 maths? I don't know. I don't know if we learn in year 10 maths. So basically, you take the relative isotopic mass. The first one's 34.97. And then I'm going to multiply with the actual percentage abundance. So you can say if you have 100 chlorine atoms, around 75.76 of them will be, we have this mass. And then you add it to the mass of the chlorine 37, so 36.97 times 24.24. So you want to take the percentage abundance into account and then just divide by 100. I mean, this is only one way to do it. I think if you're half decent with mathematics, it should be fine. But anyway, I feel like this is why I really should be in class with these ones. I could pick on the kids who are doing methods, but that's right. I do that next week. All good. And then we have 36.97 times 24.24. I'm just using a calculator. This is not methods. You can use a calculator. And so the answer is 35.45. So this is going to be the relative atomic mass of chlorine, correct to 2 decimal places or 4 significant figures. Okay, so the way that you calculate relative atomic mass is essentially you just find a weighted average, and the main difference between a weighted average and a regular average is you need to take the percentage abundance into account. So you just multiply the relative isotopic mass of each isotope with its abundance and add them all together and then divide by 100. I'm going to go with this one. Obviously, if you have more than 2 isotopes, then you have to do this more than 2 times. In the past, I've used the letter sigma for some, and that confuses everyone, so I'm not doing that again. Okay, well, that's it. That was anticlimactic. Now, once you've finished, you can find AR, just to remind everyone, in the periodic table. So we just calculated the relative atomic mass of chlorine is 35.5. So that's just a rounding to 3 significant figures. We got 35.45 before. Anyway, oh, this is just because I'm a nerd. I think I mentioned this before. So you basically can have variation in relative atomic mass, and yes, IUPAC is responsible for this, and they publish different reports every 5 years or 10 years, and to review the relative atomic masses of elements, because you actually find new isotopes in the most unlikely places. I was reading an article that found an isotope of cadmium or something on Mars or something like that, which is, quite interesting. Anyway, before I continue to ramble, let's just go through some examples. Okay, so this is the first type of question that can be asked. Element sulfur has 3 isotopes, so these are the isotopes. Sulfur 32, 33, and 34, and these are the mass numbers which you shouldn't use. You should use the actual relative isotopic masses. So sulfur 32 has a relative isotopic mass of 31.97 and the percentage abundance of 95%. Sulfur 33 is 32.97 with a percentage abundance of 0.77%, and sulfur 34 has a relative isotopic mass, used to be called RIM, like relative isotopic mass, but no, we have to change this to IR. I don't even know why. There's a technique called IR and your 12 is not useful. 33.97 is a relative isotopic mass. What's going on? And then it has a percentage abundance of 4.23%. Determine the relative atomic mass of sulfur. So the question is asking me to find AR of sulfur. Correct 2 significant figures. Okay. A good habit to start having now is to summarize the question. So this is my summary. Quickly just translated all the information. So you have 3 isotopes. These are the IR of each isotope. These are the percentage abundances of each isotope, and this is the unknown that I need to find. This is a very simple question. All you need to do is to find the weighted average of these 3. So I'm going to go 31.97 times 95% plus 32.97 times 0.77% and 33.97 times 4.23%. You have to divide by 100. If your relative atomic mass turned out to be like 3000, you've done something wrong. I'm just typing things in the calculator because yeah, I'm not doing that by hand. Please type the right thing in the calculator. That's the number 2 most common mistake in this topic. Number 1 is not reading the question and have no idea what the question asks you to find. Oh, we'll see those mistakes very soon. So 32.06 is my answer. Now I have to convert this to 2 significant figures, so it's just going to be 32. My habit, always box the final answer. It makes it a lot easier for the assessor to actually see where your final answer is and can give you that 1 mark straight away. Okay, that's a terrible working out. Let's try that again. 32.06. I'm going to write it here so it doesn't look like it's on the denominator. Equal, so 32. Final answer, corrected to sig fig. Moving on to example 2. So bromine. Now bromine's Br. Let's start by reading the question and translating the information to a summary. So Br has a relative atomic mass of 79.91. So they already give you the relative atomic mass, which is 79.91. It has 2 isotopes, bromine 79. Okay, so bromine 79, they give you the relative isotopic mass of bromine 79, which is 78.92. And this one has an abundance of 50.54%. And then the second isotope, which is bromine 81, you are not given any information on that. Okay. Try not to get too intimidated by the different numbers that are given to you. Just read the question carefully and translate and store the information into their appropriate places. So 79.91, the first number that is given to me here, this is your relative atomic mass of bromine. So that's my summary there. So I deal with this number. The first isotope, 79, this is the relative isotopic mass of it. So I've done that. And then the percentage abundance is 50.54. Okay. I don't have any information on bromine 81. Of course I don't, because that's what the question is telling me to do. So this is the unknown. Determine both the percentage abundance, so you need to know the percentage abundance, and the relative isotopic mass of the second isotope. So you can't say that the relative isotopic mass of this is 81. This is the mass number, but the relative isotopic mass is not going to be exactly that. So you have to work out what that is. So I have two unknown that I need to find: the percentage abundance of bromine 81 and the relative isotopic mass of bromine 81. And I have to leave my final answers correct to 4 significant figures. Okay, so first things first, there are only two isotopes, which means that the percentage abundance of these isotopes have to add up to 100%. So it's actually very easy to work out the percentage abundance of 81 bromine, because it's just going to be 100 minus the percentage abundance of the other isotope. You know what? I think I'm gonna... okay, that's probably wrong. Let's just use a calculator. No, that's not wrong. Wow, that's surprising. Okay, so that's that. That's already correct to 4 significant figures. Let me just write that again. Sometimes I surprise myself. You know what? I normally don't recommend doing mental calculation because I always make stupid mistakes, but that was just a fluke. So box your final answer, because this is one of the two unknowns that you need to find. So I've got the percentage abundance of bromine 81, which is 49.96%. Can translate 46. And then you need to find the relative isotopic mass now. Now you have the you haven't used these two numbers, so you're gonna have to use it. I'm gonna call it X because I'm a math teacher sometimes. So we know that I can find the relative atomic mass is essentially 78.92, which is the relative isotopic mass of bromine 79, times 50.54 plus X, which is my other unknown, times 49.46 over 100. So this is the formula for calculating the relative atomic mass. Instead of this, I'm just going to write 79.91, which is the actual relative atomic mass. So there you go. You need to solve your linear equation. I'm sure you can do it without my help, but just move the 100 over. 79.91 is this. Let's just don't round, by the way. Keep the all of the decimal places. Oh wow. Okay, so 39.886168. So I basically just did the multiplication, the brackets, plus 49.46 times x. So you want to subtract, so 7,991 minus this. So I have, again, do not round. Keep all the decimal places in your calculator. 832. So if you do a subtraction, you should get this, and then divide both sides by 49.46. You got your answer. So 80.92 would equal to x, which is good because it's BR 81, and then I'm just going to write IR is 80.92, and then I box my final answer. Okay, so yes, if you ever wonder why you need to learn linear equation, this is the application of mathematics in chemistry. Example 3. Okay, this one's actually quite fun. So copper has two isotopes. You have copper 63. Start summarizing the question. It has a relative isotopic mass of 62.95, and you have copper 65, which has a relative isotopic mass of 64.95. Okay, you also given the relative atomic mass of copper. So I know that the relative atomic mass is 63.54. What's the unknown here? You need to calculate the percentage abundance. So I do not know the percentage abundance of this one or the percentage abundance of this one. Okay, general rule of thumb. Yeah, well, there's one piece of information that is not given in this question, but you should be able to deduce, and it's the fact that there are only two isotopes. So these two percentage abundance should add up to 100%. So I'm going to call one of them X, again, because I teach maths, and if there's an unknown, I call it x. The second percentage abundant is going to be 100 minus x. Obviously, it's very obvious. You really want to have only one variable if you're going to have to construct an equation. You don't want multiple variables. You can have multiple variables if you really want to solve simultaneous linear equations. I am not in the mood for that right now. All right, so 63.54, which is the relative atomic mass, can be calculated using 62.95 times x. So this is the relative isotopic mass of copper 63 times its percentage abundance, plus 64.95 times 100 minus x over 100. Okay, now you just need to solve for x. Shouldn't be too bad. So multiply the 100, so 6,354. There's only one way to do it. You can use fraction for IK, just convert it to percentage later. And then this is 62.95x plus 6495 minus, be careful when you open brackets, 64.95x. Okay, I'm solving a linear equation. I think you should be grateful you don't get a quadratic equation. It used to be in the course, but, well, not in year 11, but they removed it. So sad. Okay, so I'm going to move the 6495 to the other side. I get negative 141. Don't be afraid, it will be fine. So I'm going to take x out as a common factor. You get 62.95 minus 64.95. Well, I'm not teaching chemistry anymore. Minus 141. That's okay. Math is fine. 62.95 minus 64. I cannot believe I just did that in the calculator. Clearly can't teach math either. Oh my god, this is hilarious. Okay, so 141 divided by 2, you get 70.5 equal to x. So the percentage abundance of 63 copper is going to be 70.50%, corrected to 4 significant figures. And the percentage abundant of 65 copper, it's going to be 100 minus that, whatever 100 minus that equal to, which is going to be 29.5. I have some self-respect, so I'm going to try and do that by hand. Okay, so there you go. That's the answer. Linear equations, so good. All right, last concept, not last concept for today, last concept for this video. Very easy, relative molecular mass and relative formula mass. So anyway, I'm not sure what's going on with the animation there. But relative molecular mass is essentially for molecules, whereas the formula mass is for ionic compounds, but they mean the same thing. And these are essentially the sum of all of the relative atomic masses of all of the atoms in the molecule or compound. And you're going to get the relative atomic mass from the periodic table. So you need to use the periodic table to get the individual relative atomic mass. Let me see. Yeah, I do have a periodic table here, so I'm going to use it so I don't have to go back to this slide. So let's give you an example. Well, two examples. This is example 4. There's another one after this. So calculate the relative molecular mass. What is this called? MR? M? This is terrible. Anyway, of each of the following compounds. So we'll start with glucose. So glucose has 6 carbon. So 6 times the relative atomic mass of carbon plus 12 times the relative atomic mass of hydrogen. I think I may not have enough room, so I'm going to set it up here. Okay, 6 times the relative atomic mass of carbon plus 12 times the relative atomic mass of hydrogen plus 6 times the relative atomic mass of oxygen. Okay, so you're going to get the relative atomic mass of carbon from the periodic table. It is 12.0. And then 12 times the relative atomic mass of hydrogen, which is 1.0, and 6 times the relative atomic mass of oxygen, which is 16.0. And because I am a very sad person, I actually know the answer is 180, and that's it. But you put it in the calculator. Remember bit mass, yeah? Multiplication before addition. Okay, urea. So you just need to be careful when you see the formula such as this. So I'm just going to say, so it depends on what you want to do. You can do NH2 and then double it, which is I'm going to do here. So it's 2 times the relative atomic mass of nitrogen plus 2 times the relative atomic mass of hydrogen. Okay, so that's the NH2 too. And then we need 1 relative atomic mass of carbon and 1 relative atomic mass of oxygen. Okay, so nitrogen, if you look at the periodic table, is 14.0. And then hydrogen is 1.0 again. And then 12 and 16. So what is this? 18, I don't know, 36. 18. Did I just say 18? I mean 16. Okay. Just put it in the calculator. Can't actually talk and do mental math at the same time. I think one of these days I just try multiplication instead of addition, so I had to try again. I hope you take less time to type these things in the calculator compared to me. But anyway, it's fine. It's fine. 60. Wow, that was a struggle. Box final answer, circle final answer. Okay, similarly, we have example 5. This is actually the easy part. I think the hard part was previous examples. So we need to find, do I have just MR, okay. MF, FR, relative, I really don't care what you use for this. So I'm just going to write relative formula mass of PbO2. So you basically need the relative atomic mass of Pb and 2 times the relative atomic mass of oxygen. So Pb is, I can never find Pb, 207.2 plus 2 times 16.0, and the answer is, really should do this in my head, but 239.2. Okay, so that's the first one. And then we do the same thing, CaCO3. So we have relative atomic mass of carbon plus, when you get very good, you don't have to write this step out, that's fine. You just write the answer, that's fine too. I do, however, normally recommend writing working out, especially if the question is worth more than a mark. Carbon's 40.0 in here. Where's carbon? 40.1. Okay, so 40.1. Let's try not to skip step in the first example. I'm just talking to myself because I do that quite often. So 40.1, not talking to myself, skipping steps, I mean. 48. Okay, 101. So that's the second one. And ammonium sulfate. So once again, you want to be careful when you see the brackets. So it just means that you have to double everything. So 2 times the relative atomic mass of nitrogen, which is at the end, and then the H4 is 4 times the relative atomic mass of hydrogen, plus the relative atomic mass of sulfur, and 4 times the relative atomic mass of oxygen. Okay, I'm gonna squeeze in here 14 plus 4 plus 32. Do we go with 32.1? I think so. 32.1, yep. And 16. Okay. So 2 times, because I really can't do math, I'm gonna do plus 32.1. Okay, so 84.1. I think I need to obtain a list of students who are doing year 12 methods so I can pick on them. Okay, I think that's it for this video.